Now let's talk about the multi-core system. So far what we have discussed is that we have this processor chip and being sit on the motherboard separately, one processor, two processor, three processor, like there may be like 16 processors, stuff like that. They are connected to some common network, maybe a bus system, and this bus also connected with the memory subsystem, IO subsystem, etc. But they're happening on the board level. If you open up the computer box, you will see on the motherboard those components are laid down, right? A multi-core system is something like, you imagine you take this system from the motherboard and put the whole system in one single chip. Okay, sometimes it's called a system on chip as well. It's called SoC, system on chip. So idea is that since we have this technology to shrink in more and more devices onto one single piece of silicon, instead of having one chip for one processor, why don't we just bring in the whole system, like multiple processor, two processor, three processor, not three usually, 2, 4, 6, 8, that kind of processor together in one single chip. And they are your multi-core organization. When we talk about multi-core, each core is an individual processor. Okay. So overall, this multi-core organization can be characterized with couple of parameters. Number of cores on the chip, like it's a dual core, means there are two processors inside it, one single chip, or 4 quad core, 8 core, there are 16 core, there are 64 core. It's not that uncommon for enterprise kind of system. The number of level of cache memories, like in the bus system, we have already shown your L1 and L2 cache, which is a local memory. You can, for time being, just think caches as a local memory. They can be more very interesting set of local memories connected in very interesting ways. An amount of shared cache memory. Let's say there can be like maybe two processor is sharing one local memory, another two processors sharing another two local memory. Lot of different configuration can be done, and couple of them we can see as, let's say there are n cores, and each of them dedicated L1 data cache or local memory for the data, and dedicated L1 instruction cache. Like that, each of them are L1 are on the chip in this picture. These cores and the L1 memories, local memories, are residing on the chip, whereas the L2 level 2 local memory is residing on the board, and then this L2 is connected to the main memory. And of course on the board it has the IO. So basically your full chip contain multiple cores with level 1 local memory, and this local memory also separated out, for one for data, another for instructions. Now there can be another configuration where your L2 cache goes inside the chip, inside one processor. So if you open up the board, you see one processor chip and one main memory chip, and of course the IO connections are there. But inside that processor, you have multiple cores connected to their L1, separate L1 data local memory and L1 instruction memory, and then these L1 memories are connected to the L2 cache, which may contain both data and instructions. And instead of having one common L2 cache as a previous example, this example, each core is enjoying their own L2 cache. Okay, that can be one configuration. That configuration continues. Maybe like L1 and data cache and instruction cache are separate, and each core enjoys their own local memory such that, but all the cores shares one L2 cache. Or we can combine and give an L3 cache, whereas L2 caches are dedicated to each of these CPU cores, but L3 cache is basically shared between the CPU cores. So that can be like, it's all depending on the market need and your performance need and what kind of problem you are solving. There can be separate different configuration for these multi-core organizations. So the software performance, what is the impact on that? The potential performance benefit of a multi-core organization depends on the ability to effectively exploit the parallel resource. So let's say you have a single program on this single instruction, single data system, just like a traditional classic computing system. The speed up really depends on how much of the program you can actually break it down into small pieces so that these small pieces can be executed in parallel, in concurrent with each other. So your speed up really bound to that point, and we can apply Amdahl's law into that. Let's say you're out of 1 as a whole program, only f fraction can be parallelized into n ways. That means your speed up by Amdahl's law is of course 1 by 1 minus f plus f by n. Okay, and also remember, when we split up these programs, we call it a single thread program in just in a common terminology, into the multi-thread program or multi-process program, there will be interdependent on those smaller blocks of or modules in between them, and they might start waiting on one another, right? So your speed up may not be truly f divided by n in this case. Translating single processing, single thread programs into multi-thread program is a really tricky business. So I hope all of you will go through that parallel processing class and parallel programming class, if you have not already done that, to get yourself familiarized with this concept of how you can divide a problem into multiple parallel problem, where these multiple parallel problem are least dependent on each other. There will be dependency, there will be data dependency between these parallel modules, but how to divide a program in such a way these parallel blocks or parallel modules data dependencies are minimized. That's the whole challenge in making a parallel program work.